So today we're going to be looking at scalar multiplication. Now, scalar multiplication is going to be a new term that we're going to be using when we multiply a matrix. It's going to be called scaling a matrix. Now, full definition would be calling it scalar multiplication because there are different forms of it. But this is not the same thing as what we call matrix multiplication. We're not multiplying one matrix times another. We're multiplying one matrix times a scale factor, which means we are in essence dilating or making that matrix go through dilation. So let's take a look at how that actually works. Well, when we apply a scale to a matrix, let's say I want to scale this matrix by 2, I quite literally take each element of the matrix, the -4, the 2, the 7, and the 12, and I multiply them all by 2, and I get the new matrix. That's it. So without taking too much time, let's go ahead and jump into this. So for things like number 1, if I want to scale this matrix by 2, I'm going to get an answer of each one of these multiplied by 2, so I'll get an 8, 0, -16. If I want to scale a matrix by 0.5, I just multiply each of these by 0.5, so 7, 1, 5. Awesome. If I want to multiply this matrix by -3, I just multiply all the numbers by -3. So that will give me a 36, a -24, and a 3. If I want to scale this matrix by -0.5, I do the same thing. Each one of these multiplied in half and change the sign. So 1, 5, 0. Awesome. Now, the 3 by 1 matrices work the exact same as the 2 by 2, as the 3 by 3. So why don't you go ahead and take a pause in the video, try number 9 and number 12, and see how well you do. Unpause it when you're done and check your work. Okay? Now that you've had a shot, I'm just literally multiplying each element inside this matrix by the scale factor of 9. So 18, 36, -27, and 9. Boom. That's it. If I have something like this, I'm just cutting each of these numbers in half. So I'm going to get a 3 by 3 matrix where each of my numbers is cut in half. It's going to be 1.8, 5, 4.1, 0.9, -2, 0, -4.1, -0.7, and 1.5. Awesome. Easy enough. The only issue you might get to, and at this point I really don't think it's going to be too big of an issue, is what happens if I scale and then I add? Well, the first thing I'm going to look at is, are these two matrices the same dimensions? Well, this is a 2 by 2, this is a 2 by 2, so yeah, it's not going to be a big deal. I'm going to scale this first matrix by 2, and I'm going to get a -10, 2, -16, and 24. And I'm going to add these numbers to my previous 1, -8, 4, -1. That's going to give me a final answer of, let's see, top left, -9, top right, 6, bottom left, bottom right. Boom. There we go. So why don't you go ahead, now that you've seen one in action, try the next one. Looks like we've restarted the numbering system, so let's try number 3 real quick. Okay. So now that you've had a chance on number 3, let's take a look. So I'm going to distribute this all by 5. Now, you have two options right here. I could either distribute a 5 and keep the minus between them, or I can distribute a -5. But if I've pushed the negative into the matrix, I will not have a negative out here anymore. So the first thing I'm going to do is I'm going to drop this down because I'm not touching the first matrix at first. And so you have an option of distribute the 5 or distribute the negative. I'm going to distribute the -5, and I'm going to multiply all of these by -5, which means there is no longer a negative on the outside. That will become a -55. That will become a +60, a -10, and a +65. And you'll see that what I could have done, if I only distributed the 5, I would have -55, -60, -10, and -65. Doesn't matter which way you did it, as long as you do it consistently. Either put the negative in all the way, or leave it out all the way. So my final answer here is top left, negative 53, top right, 53, bottom left, 8, bottom right, 75. There we go. Perfect. So that is going to bring us to the next part. So now here is we're trying to find the missing scalar. So quite literally what you can do is there's several ways you can do it. Finding the missing scale is the same on each one of these terms. So it could be we're looking at the top left, the top right, the bottom left, or the bottom right. Doesn't matter which one, because the scale factor is going to be the same across all of them. If I look at it and say, okay, what was scaled the negative 4 to make it a 12? Well, that's probably going to be, let's take the 12 divided by negative 4. We'll get a positive 3, or sorry, a negative 3. That's going to be the same across all 4 terms. I could say, what times 2 gave me negative 6? Why don't I take the negative 6, divide it by 2? I'll get a negative 3. In fact, each part of these, if I divide the individual pieces of the matrix, not matrix division, I'm checking to see what I scaled the matrix by to produce the new thing. Not division, checking the scale. So I know that my scale factor looks like it is a negative 3. So how would I go about doing that? Like if I looked at number 15, what I'm going to do is I'm going to say, okay, what times 12 gives me 24? I could say that's a 2. Now, what I could do is I could try and verify and say, okay, what times negative 10 is negative 20? Well, that'd still be a 2. I could say, what times 4 gives me 8? Well, that would still be a 2. No matter which answer you pick, A is equal to 2. If I look at number 18, I've got 4 different things that I can check. I only really need to check one of them. What times negative 2 is positive 2? Well, it sounds like G is a negative 1. I could check another one. What times 14 is negative 14? Well, again, negative 1. I could say, what times 2 is negative 2? Negative 1. I could say, what times 11 is negative 11? I could say, negative 1. Again, it doesn't matter which one you pick. All of these are your individual answers. G is equal to negative 1. So having said that, why don't you take a quick look at number 21, figure out what the scale factor is. Okay. Now that you've had a moment, no matter which one you picked, we're going to randomly pick, let's say, the bottom center. I'm going to say, okay, I'm going to look at this as x times 4 gives me a negative 2. So if I divide both sides by 4, x is negative 2/4 or negative 1/2. If you want to put it as a decimal, negative 0.5. No matter which part I check, 6.4 times negative half, negative 1.2 times negative half, negative 8.2 times negative half, I get the same scale throughout. So I know that my overall final answer is that x is equal to either negative 1/2 or negative 0.5. Awesome. So this one's a little more complicated. Again, not really sure why we renumbered the numbers here, but we're going to go with it. Why don't you go ahead and try out number 5. Unpause the video when you're done and see how well you did. Okay, so what you might have noticed is there's a couple ways to work this. Some of you, what you might have done is you might have moved that matrix over here by subtracting it, which is a valid way to solve it. I could subtract 15, 0, negative 12, and 1, so that I can set this up just like what we did previously and say, okay, E 6, 21, negative 2, 16 is equal to 33 minus 15, which is going to be 18. 63 minus 0, negative 18 minus negative 12, so that's plus 12. 49 minus 1, which is 48. And then you could have looked at it just like we did previously and say, hey, any one of these, 6 times what is 18? And you would have gotten an answer of E is equal to 3, no matter where you went. Or what some of you might have realized is you can kind of create your own mini equation. What you could have done, let's box that up, is I could have said, how about I just look at the top left? Say plus 15 is equal to 33. If I'm only looking at the top left of this matrix system, this is E times 6, or I could say that is 6E plus 15 is equal to 33. And I could have solved the top left and gotten that. So let's zoom out just a bit so we can keep this all in frame. Subtract 15. 6E is equal to 18. E is equal to 3. So either way, if you want to move the matrix over and solve it that way, or if you just want to pick part of the matrix to solve for that missing scalar, they both work. And that's it.